the ICECP talk about an information-centric compute platform that we have built over the past couple of years. And I'm going to start off with a quick introduction on Internet of Things to just really level set everyone on. I'm not taking this to a technical level here, but more to business value of IoT. And what we see a lot, what we hear a lot about IoT is we're collecting a lot of data, we're trying to connect all kinds of sensors, and we're doing some fancy analytics, or we're doing machine learning, and then we are at the point where the discussion pretty much stops at what are we going to do with all the data? What are we going to do with all the results that we're doing? What is the impact of the outcome of the analytics? And that's why I have this third bubble here where I put trusted actionable intelligence in. And I underlined the two important words here, and that is trusted and that's actionable. Trusted means whatever I'm getting out of the analytics, everything that my environment tells you, I have to put a certain amount of trust in that so that I can make any decisions based on the result of the analytics. If the analytics tells me, turn this valve on and something crazy is going to happen, then I have done a good amount of IoT. I've collected data and I've run analytics and it tells me what to do, but it's not trusted because I don't know what is going to happen when I do that. So if this is not, if the data that I'm putting in and the analytics that I'm running is not known what the result is, then I have a problem here. The second part is, after munching all the data, if I can't make a decision what I'm getting out of that, so if it's not actionable, then I just have a huge data collection machine here. And I can't have an impact on the environment because IoT is being done to have an impact on your either production environment or on the system that you're instrumenting, the environment that you're instrumenting. So really trusted. Do I know what is coming out of that and why it's coming out of that? And actionable is, can I take some actions? Can I actually change the environment based on that data? Another trend that we've seen over the last couple of months in IoT is that we are seeing more of the IoT is moving closer to where the data is being collected. And I've put a couple of keywords out here, starting from perpetual analytics. That means I'm constantly analyzing the data that I'm getting, and I'm constantly making informed decisions based on the data that I'm receiving. I put things out like latency, because if I'm collecting data from a physical environment, sometimes I have requirements that I really quickly respond to changes in the environment, to changes in the data for safety reasons, for example. If you have like a large rotating engine and something is going to happen to the bearing of that engine, then you want to respond to that very quickly. And going to cloud environments or going to large data centers that sit somewhere on the other side of the world might be way too long to respond to that information. And you can't always send all the data up to where it's being analyzed, especially the more data we are collecting. I put security and privacy out there. Security is one side that I want to prevent that someone is using my IoT installations to get into my environment. But it also means, and that brings me back to the trusted actionable, to the trusted analytics, the trusted intelligence, is, do I really know where my data comes from? If I'm collecting temperature sensor data and I think it comes from a particular room, is it really the temperature that's in that room? Or is someone creating fake IoT data here and telling me, hey, your room is way too warm, you should start your AC? Or privacy. With the kind of ever-increasing, ever-improving algorithms, what type of information can I extract from really baseline information that I'm collecting? So if I understand, for example, the temperature in hotel rooms, can I derive the capacity and the utilization of that hotel? Can I derive how well that company is doing? And so these are all things that are starting to have an impact on how do I guard my information? How do I move my information around? How much does the solution cost? What is the result of that? Because if I'm creating an IoT solution that from a setup is rather cheap, but it's really costly to guard the information and the impact on my environment is not that high, then I might actually be better off to not build such a solution. So what's the return on investment that I have here over the long term? So that means I want to iteratively combine a solution that I'm starting off small with more and more environment. And I have shown that here in the part that says interconnected IoT solutions, because as we go along, we see that more and more of those isolated environments are getting connected and are getting used together. So what does that iterative approach really mean? So when I start off with where does my information come from, how and where is my information manipulated, starting off with the small solutions, what results are produced of that and what action is taken there. So once I have done this, starting, let's say I've taken a proof of concept into an actual small scale IoT solution that gives me results, now I'm getting hungry for more data. So I'm iterating over this environment and I want to scale up. I want to add more functionality to it. So I want to exchange components. I don't want to restart over and say, okay, version 2.0 is going to be much better than version 1.0, but let's throw everything away that we did in version 1.0 because it was only a test. So that's why I'm putting this out here as in kind of, we really have to think about that iterative approach to IoT solutions to slowly grow and expand that and interconnect it with more and more infrastructure. So from here on, I want to go a little more into details about the technology that we've been using and with an information-centric approach. And when we look at conventional solutions, conventional internet-connected solutions, the first part is when I ask, so where do my bits typically come from? I use something like a URI or a URL that points to a particular server or a particular location on the internet. And I've given that example here with an HTTPS connection and a port and says, hey, if you want that information, go to that particular host. Yes, you can use a name if you want to make this more readable, but in the end, it always boils down to a particular connection to one single or a set of endpoints that provide that information. And that is kind of like shown here in that where I take this apart. But what I really want is access to my information. I don't want to know the name of the host that's going to provide me that information. So that is where we are looking at how can I express access to the information that I say, hey, I want to have Intel built the information from the Intel side, from a building. And we call that JF3. And it's in the second floor, room 20. And there I want the temperature. So I don't want to know that it's served by 10.1.2.3, or if I'm using IPv6, this long number of an address. So this also has another problem, that if for some reason that servicing host is gone, it's changed, it's compromised, all the data that I have on that is gone. So which we see today is when companies are getting acquired, when things are changing, you have all those dangling references into the internet that are essentially pointing into the big void. And it's really difficult to find what was the data that was being behind that address. If you look at that information from the shift from that host-based approach to an information-centric approach, then we are shifting away from the address, that means from the where the information is being served, to the what and how it's named. So in our example here with ICECP, with our solution, we've gone to a similar scheme, but you see there's no host in there anymore. So we're just giving the temperature data from that room a name. And every time you want to have information about that room, you are requesting information from that name. So the host is really irrelevant here, and that's an important thing to take away from an information-centric approach. Is the host that is serving that information is irrelevant. The same type of data can be served by anyone who has it. So I added this additional functionality because it immediately comes to question. So if everybody can serve the temperature, how do I know that it's actually correct? And that is where we have a lot of cryptographic means to main the authenticity of the original data. So here, as you can see in that hourglass, we're now having, instead of an IP address as the center, as the bottleneck, or the center of that hourglass where everything goes through, we have content chunks as part of the center that everything maps to. So if I want to get some piece of information, so I'm requesting what we call objects here. So, and an object is essentially a contextual representation of things such as sensor data. It could be binary code, it could be scripts, it could be containers, images, videos, everything. Again, I'm using the same, and that's also an important part, I'm using the same way of addressing that type of information as I've shown up here in that URL to get an object. So if I want to have a piece of code, I'm using an address and a unique name for that piece of code. I don't care where it actually comes from. We've looked at different implementations for information-centric environments, and we came to what's called the named data networking NDN. You can go out to the internet and look at namedata.net, and you will find more information about those basic concepts. So as we see from an IoT perspective, it really maps well to how I get my data that I want to work with, because I want to operate on a particular set of information. Let's be the temperature, let's be its sensor data. But I also want to know like a particular algorithm. If I can name and give an algorithm or an instance, an implementation of a particular algorithm, one unique name, then I can say, I want to have an implementation that maps that algorithm, give it to me as an object, and I will execute those. So how do I get to that information? So the consumer starts to express what we call an interest in an object. So this interest travels through the network. There are a couple of helper applications, helper tools that help that move that interest along the name path and essentially routes this through the system. If the interest can be satisfied along that path, then the object is immediately returned to the requester. So that means the object can come from an originator, from whoever created that object. So if I want to have the latest temperature sensor from a thermostat, then it's very likely that this comes straight from the thermostat. If I want to have an object, for example, a piece of code that was created half a year ago and has been distributed because the platform has already executed that functionality like an algorithm, then it's very likely that it will come from somewhere close by. So if you think about that, with those two primitives, we can create very powerful content distributions and semantics. Additionally, since all those objects are retained in the network for their specific time to live, I have a seamless way of handling in transit and at rest operations on those objects. So how do we build such a platform? 4 ground rules out. The first is we should go with a very minimalist approach. And I have worked a long time in microkernels and small operating systems where the same primitive or the same approaches have been taken. And I really like that quote by Dave Wheeler that says, all problems in computer science can be solved by another level of indirection, except the problem of too many layers of indirection. So let's try to really focus on those 3 things. Don't create a large set of APIs, set of functionalities. So first is clear separation of mechanisms and policies. A mechanism is something that allows me to do or to work on, let's say, an object or perform a particular piece of action. Policies tell me how I have to do this. For example, a mechanism would be to send an object from location A to location B, or to get access to a temperature data. The policy would tell me whether I can do this or for how long I can retain that information. If I'm separating those 2 pieces, then I can have my underlying framework implement those mechanisms, and I can adjust my policies later on when I deploy that infrastructure, when I deploy that framework. From an IoT perspective and from an IoT infrastructure perspective, this is a very important key point, because as we see that legislation and legal frameworks are being set up and being drafted as we speak, I might have to change what's possible with the data as my system is in production. So I might get grandfathered in that I can send a particular piece of information from to a particular country, but I should not hope that this is always the case. And we've seen this in many places around the world, that countries says, if you collect a certain type of data, that piece of information cannot leave the country. You have to store it within the borders of this country. And if you don't have your policies explicitly expressed, and they're somewhere implicit in your environment, you would have to go and change a lot of code to make sure that a particular piece of data does not leave your country. You might not even have the notion of a country in your abstractions. So if we can separate mechanisms and policies, we can always adopt those policies. The second bullet down here, or the third bullet, around core abstractions. We want to build a composable system. So starting off with a small part, and we want to extend this. We want to build infrastructure on top of that by composing individual component entities. That means I have to have my abstractions really orthogonal. If I don't have orthogonal core abstractions, if I start to compose them, then I'm getting very interesting, to say it that way, very interesting behavior. And it can be, for example, from a security perspective. If I have one abstraction that says who has access to a particular object, and it's handled one way. So now I'm having the option to transfer an object with a different pattern to guard that object. So now if I'm putting those 2 pieces together, I'm not really clear in that composed infrastructure or a composed environment, whether I still have access to that or not, because I might go around one way and I have access, but if I'm using a different API to pretty much achieve the same functionality, then I might not have access. So this is, and we've seen that in past systems where the abstractions are not orthogonal, and once they are being put together, there are lots of conflicts, and it's very difficult to resolve this in a homogeneous fashion. and coherent fashion. And then the last bullet down there is inheritance and delegation versus implicit assumptions. Infrastructure today is often being built around some implicitly coded policies. I already touched a little on that when it came to separation of mechanisms and policies. So if I have implicitly coded that I have to use a particular crypto algorithm, if that changes because the particular algorithm has not been considered or is not considered strong enough anymore, if I cannot make those changes explicitly, or I can explicitly say what functionality is being used, then I have to go in and make those changes, and I have to adopt my system, and it's a very costly process, and I also don't know which parts of the system have changed and which part of the system have not changed. So always try to make your policies explicit, because then it also allows us later on that if we can delegate functionality to go more toward local orchestration, so that I can specify an environment to actually take care of itself. And that is bridging back to one of my original slides, or the second slide, is more functionality being executed at the edge. More functionality is becoming more autonomously controlled at the edge, because I don't always have the ability to control that functionality. We built a system using a plane-oriented channel architecture, where you have access to those objects, two planes, using a homogenized channel API. So you can have access, or you can open a channel and you can request objects on that channel. The channel is a representative of a name for one or multiple objects. This allows us to build also a coherent security story around those objects, because if you have exactly one control point how to get to those objects, then you can control that at one place. So you either have access or you don't have access, and the question how you can control this is through some of the same mechanisms that you have. So depending on how you get to the data, and you can consider that in those planes, we're starting at the bottom with a data and analytics plane, manageability, communication. So who can communicate with whom, for example, what network what network connections are being used in the communication plane. As our objects travel within the plane, I can use functionality to influence the different planes. So if I have, for example, if I have analytics that analyzes, or an analytics object that analyzes the flow of certain objects, and I get the result that something is going on in my environment, for example, because too much data is being sent, I can take that result and influence the control or the communication plane and say, start throttling the objects that are being sent. Plane-oriented channel architecture, just to summarize this, what I just said, plane access, we're using an abstraction as a channel. You can publish and subscribe on those channels, and use that for a scalable object distribution. Long term, there's also the idea of going with a more probabilistic QoS-driven access model to those channels. And the reason for introducing more probability here is that somewhere in the system, nothing is guaranteed at 100%. And if I'm constantly, perpetually collecting information, that means I might be able to deal with a loss of some of that information. For example, if I'm collecting temperature data at a 1 or 2 second interval, this is perfectly fine if I'm losing 20% of that information. So if that helps me to better utilize my infrastructure, that is where a probabilistic approach makes a lot of sense. For the objects that are we being transferring, we're requiring that they can be interpreted without inside knowledge. So that means, again, maps to the explicit and implicit way of dealing with with expressing policies and stating what an object is. So I always have the ability to say this is a particular type of an object, and I can look up what operations I can do with that. And finally, not only we're talking about objects, but also object metadata that allows me to that is processable and extensible. So I can find out what a particular object is, and through that metadata, I can infer information about the object. We built a system here that looks a little like an infrastructure that you take puzzle pieces that are very, very similarly structured and combine them into a larger piece of infrastructure. So modules that are those puzzle pieces here, and I've denoted that with the F with here as in this yellow puzzle piece with functionality, are being connected. They all have a set of input and output channels where that can be configured, where they take in objects and where they create output objects. They have a configuration channel. Again, we're using the same primitives here to configuring those objects, because that configuration channel could be the result of another building block, another of those puzzle pieces, for example, some machine learning. So I could have a machine learning yellow block that creates the information for the configuration attributes of another block. And if they change, I can reconfigure that functionality block automatically. And on the other side, a status channel allows me to find out information about what this block is doing, how many resources it's being using, and just general information about this block that I can evaluate whether I need to, for example, scale out with my infrastructure, that I need more compute capacity if one of those blocks says it's starting to overload the system. So really designed for a dynamic and adaptable infrastructure. Well, how do I build a solution out of those building blocks in ICECP? Essentially, you're just puzzling those pieces together. And because think of this as a data flow driven architecture where my modules are getting connected. Ideally, in the long term, you want to be able to dynamically connect those and reconnect those. The location of a particular module is purely determined by policy. So I can move those modules around in my infrastructure. So if I'm starting off and I want to collect a lot of data collect data at the edge, but I want to do processing mostly in the cloud. So more like a traditional infrastructure that we see today, then I can run the very same building blocks in a cloud environment. And as I realize and as I look at the status information of those blocks, I see how much data is how many objects are being transferred from the edge to the cloud. I can calculate, I can derive that it might be better to move particular functionality to somewhere closer to where the data is being collected. And I can do this without really restructuring the environment, without restructuring my solution, because I'm looking at a purely data flow driven architecture. One more drill down into the architecture. We have some of those that information out on the URL that you can see at the top at GitHub. All the software is open source, so you can go there. There's a lot of documentation out on that GitHub website. And we've built this using a Java 1.8 JDK-based solution. It's all integrated with Maven builds, and we have several repositories there. So if you're interested in going further into details, that would be the address to go. Thank you, everyone, and I hope this was informative.